Hey everybody, welcome to another video, and today we'll be doing optimization using differentiation. So we have the following question. A cylinder must have a volume of 500. Determine the height and radius that will minimize the materials used. So when the question is asking for materials used, we know that we're going to be dealing with surface area. And it's very explicitly telling us the volume. So with optimization, you always need to find two equations. So one of our equations is going to be the volume, and the second will be surface area because we're being asked for the materials used. So our volume for the cylinder is volume is equal to pi r squared height. But since we already know the volume, we can substitute 500 for the volume. Now the surface area for the cylinder is as follows. The surface area is equal to 2 pi r squared plus 2 pi r times height. We have the 2 pi r squared because we have two circles, and the area of each circle is pi r squared. So we add the 2 because there's two circles, and then the whole middle area is just two radiuses times the height. So we have the 2 radius, the height, and the pi because it's a circle. So now what we want to do is we want to solve for one variable and then plug it into the surface area equation because we're being asked for the materials used. So over here, we can easily solve for h. So we're going to have height is equal to 500 over pi r squared. So now we have our height. Now we can put this into our surface area and then find the derivative to determine where the radius will be the smallest. So we're going to have surface area is equal to 2 pi r squared plus 2 pi r times 500 over pi r squared. Now we can do a little bit of simplification. We're going to get surface area is equal to 2 pi r squared. One of the r's is going to cancel out. The pi is also going to cancel out. So, and the r is also going to cancel out here. So we're going to have 1,000 over radius. Okay, great. So now what we can do is find the derivative with respect to the radius to determine where the radius is going to be the smallest. So we take the derivative with respect to r. So here we're going to have the derivative of surface area with respect to the radius, and then we just use the power rule here, so we bring down the 2, so we have 4 pi r minus 1,000 over r squared. Okay, so now what we want to do is we want to set that derivative is equal to 0. So we set it equal to 0, and now we just have to solve for r. We're going to have 4 pi r is equal to 1,000 over r squared. Now we can cross multiply, so we're going to get 4 pi r to the power of 3 is equal to 1,000. Divide by 4, so we're going to get pi r to the third is equal to 250. Then we have to divide by pi, so we're going to get radius to the power of 3 is equal to 250 over pi. And then we take the third root, so we're going to get radius is equal to the third root of this whole thing. So okay, so now we found the minimum radius. We found the minimum radius to still achieve the volume of 500. So now what we can do is just plug this back into our height. So we're going to get height is equal to 500 over pi, and then it's a lot of algebra here, and we're going to have third root of 250 over pi to the power of 2. So now we can simplify this. So this is going to cancel out. We're just going to have a normal root. So we're going to get height is equal to 500 over pi, and we're going to have 250 over pi to the power of 2 over 3. And yeah, so this will be our height, and this will be our radius. We'll achieve, if we plug this back into the volume equation, we're going to achieve the volume of 500, and this will result in the minimum number of materials being used. Thank you. I hope I'll see you in the next video.